addition rule. The addition rule of probability is when we're looking for the probability of some event A or some event B. Or as it pertains to probability, pretty much means addition. The other way we can see it, and I guess you would say the more appropriate way, is that we have the probability of A union B. All right, this means union. When we're looking at the addition rule, we have two situations. We have what's referred to as being mutually exclusive also sometimes called disjoint. All right, in this case, we have two events that are happening that have no overlap whatsoever. We have an event A and an event B, and if there's no overlap between the two events, that's when we can just say it's the probability of A plus the probability of B. When the events are not mutually exclusive is when it generates the problem, or the more difficult aspect of the addition rule. When the two events are not mutually exclusive, so they are not mutually exclusive, there is some sort of overlap. So we have probability A, we have events A and B, but there's some overlap right here. So when we do that, we find the probability of A plus the probability of B, but then we have to subtract the probability of the intersection of A and B. And this symbol means intersection. Now, let's look at how the addition rule works. So for my first example, we're going to look at a situation where they are mutually exclusive. There is no overlap. All right, and we've looked at a situation like this before for the counting principle and also for sample space. All right, let's say specifically, we want to know the probability of rolling a 4 on a number cube or flipping heads on a coin. These two things, since I'm rolling a die and flipping a coin, there is no overlap. They're two completely separate events. All right, so the probability of rolling a 4 is 1 out of 6. There's 1 4 on a number cube, 6 total numbers. Flipping heads is 1/2. All right, so if I'm rolling a 4 or flipping heads, it's one or the other, so I add them together. Now, these are fractions. In order to add fractions, I have to have common denominators. So I'm gonna multiply the bottom by 3, and whatever I do to the bottom, I have to do to the top, which now gives me a common denominator and lets me add my probability. So 1/6 plus 3/6 is 4/6. This reduces, so I end up with a probability of 2/3. I have a probability of 2/3 of either rolling a 4 or flipping a coin and having it land on heads. For my next example, example 2 and 3, I'm gonna use the same spinner for both of them. Let's look at another example where it is not mutually exclusive. Let's look at an example where it is mutually exclusive. All right, let's say I want to spin the spinner, and I want to know the probability of it landing on a 5 or an even number less than 5. All right, so we have two events. We need to check and see if they are mutually exclusive. So I have the probability of spinning and landing on a 5, and then an even number less than 5. So 4 and 2, there is no overlap between 5 and an even number that is less than 5. So in this situation, I can just do the probability of landing on a 5 plus the probability of an even number less than 5. All right, so the probability of landing on 5, there is 1 5 out of 8 numbers, so that is 1 out of 8. The probability of an even number less than 5, I have a 4 and a 2, so that is 2 out of 8. When I add these together, I end up with 3 out of 8. So my probability is 3/8. I have a 3/8 probability of either spinning and landing on a 5 or an even number that is less than 5. I am 90% sure that I use 90% to let people know I kind of know what I'm talking about. For example 3, let's look at a situation that is not mutually exclusive. Let's say I'm looking for a probability of a number that is greater than 5 or an even number. Those are the two things I'm looking for. Now in this case, there is some overlap. All right, numbers greater than 5 include 6, 7, and 8. Even numbers include 2, 4, 6, and 8. 6 and 8 are my two overlaps. So when I find the probability, I have the probability of event A, which that's what I'm going to call a number greater than 5, plus the probability of event B, which is what I'm calling an even number, minus the probability of A with the intersection of B. So when I start doing my probabilities, numbers greater than 5, 6, 7, 8, that is 3 out of 8, plus the probability of B, even numbers, 2, 4, 6, and 8, that is 4 out of 8, minus the intersection or the overlap, 6 and 8, that's 2, so minus 2 out of 8. So when I add these together, then subtract by the intersection, I end up with 5 over 8. So the probability of spinning and either getting a number that is greater than 5 or an even number is 5/8. Another way I can do this same problem that looks a little bit different, but I can set up a Venn diagram. So I know there's a total number of outcomes. I know that this is A and this is B. All right, so circle A, circle B, event A, event B. So the overlap, there are 2 that overlap. I know that there are 3 in event A, so if I've already got 2, that's 1. So there's now 3 inside of event A. B is even numbers. There are 4 even numbers. 2 is already in there, so that's 2 more. And so in this case, it's 1, 2, 3, 4, 5. So I have a 5 out of 8 chance of getting one of those things I'm looking for. My last example for addition rule is another situation where there is an overlap. These two events are not mutually exclusive. So what is the probability of choosing a red card or an ace from a deck of cards? If you don't know what cards are in a deck of cards, Google it, you can figure it out. But there are 26 red cards in the deck and there are 4 aces, 2 of which are red, so there's my overlap. So if I look at the probability of event A, which is going to be choosing a red card, so I'm going to put an A up there, plus the probability of event B, which is choosing an ace, minus the probability of A union B. So the probability of choosing A, so the probability of choosing a red card is there's exactly 26 out of 52 red cards. The probability of B, which is probability of choosing an ace, there are 4 aces out of the 52 cards, minus how many aces are red. 2 of the 4 aces are red. So I have the probability of choosing a red card plus the probability of choosing an ace minus the probability of the 2 red aces. All right, so I end up getting 28 out of 52. As always, we have a fraction. Fancy math people at some point decided we have to simplify all fractions. So I want to know what the greatest common factor of 28 and 52 is, which in this case is 4. And so that gives me 7/13. So 7 out of 13, or 7/13 is my probability of choosing either a red card or an ace.